the vast darkness between the stars, there are worlds that have never seen a sunrise. For centuries, astronomy taught a simple rule. Planets orbit stars. Earth circles the Sun. Jupiter circles the Sun. Every known planet belonged to a stellar family, bound by gravity and warmed by light. But in the late 20th century, scientists began to realize that this picture might be incomplete. Computer simulations of planetary formation were producing a strange and unsettling result. When astronomers modeled young solar systems, the simulations rarely settled into calm, orderly structures. Instead, they became chaotic. Giant planets pulled on each other's orbits. Worlds collided. Others were flung outward at enormous speeds. Some were thrown so violently that they escaped their stars entirely. At first, these planets existed only inside equations. No telescope could see them. Without a nearby star, they reflected almost no light, and without nuclear fusion, they produced none of their own. If such planets existed, they would be nearly invisible. The idea remained controversial for years. Many astronomers suspected the simulations were exaggerating instability. Others argued that nature might simply be more violent than the solar system suggested. Then, in the 1990s, a new observational technique began to change the debate. Astronomers launched large sky surveys designed to monitor millions of distant stars at once. These projects, such as the Optical Gravitational Lensing Experiment, known as OGLE, were based on a prediction from Einstein's general theory of relativity. Gravity bends light. If a massive object passes between Earth and a distant star, the object's gravity briefly magnifies the star's light. The star brightens for a short time, revealing the presence of an otherwise invisible mass. This phenomenon is called gravitational microlensing. At first, the technique was used to detect stars and planets orbiting other stars. But hidden among the data were strange signals, short flashes of light that lasted only hours, sometimes minutes. They came from objects with planetary mass, and there was no star nearby. By the early 2000s, astronomers began publishing the first serious evidence that planets could exist completely alone in space. According to statistical studies supported by NASA and the International Astronomical Union, the Milky Way may contain hundreds of billions of these isolated worlds, planets that wander through the galaxy in permanent night. The discovery forced scientists to confront a possibility that once seemed absurd. Planets do not necessarily belong to stars. Some are cast out, becoming cosmic drifters traveling between the stars for billions of years. And understanding how these lonely worlds are created begins with a deeper look at the chaotic birth of planetary systems. Long before astronomers ever detected a rogue planet, the first clues appeared inside computer simulations. In the late 1980s and early 1990s, planetary scientists began using increasingly powerful computers to model how solar systems form. The goal seemed simple: recreate the birth of planets from a rotating disk of gas and dust around a young star. But the results were not what researchers expected. Instead of forming calm, stable systems like our own, most simulations quickly descended into chaos. Newly formed planets did not stay neatly separated in their orbits. Massive worlds pulled strongly on each other through gravity. Their paths stretched, tilted, and crossed. When three or more large planets interacted, the system often became unstable. The outcome was dramatic. One planet might spiral inward toward the star. Another could be pushed into a distant orbit. And sometimes, one planet was accelerated so strongly that it escaped the star's gravity entirely. By the early 1990s, several research groups studying planetary dynamics were reporting the same pattern. Planetary systems did not naturally settle into harmony. They began crowded, violent, and unstable. The simulations suggested something radical. Many planets should be thrown out of their systems during the early stages of formation. These worlds would not orbit any star. They would leave their birth systems at speeds of several kilometers per second, entering the vast emptiness between stars. Once gone, gravity from the parent star could never pull them back. At the time, the idea sounded extreme. Astronomers had never observed such a planet. Without a nearby star to illuminate it, a wandering planet would be almost impossible to see with traditional telescopes. Even so, the physics behind the prediction was solid. Planetary systems form in crowded environments, often inside star clusters, where young stars pass near each other. A close stellar flyby can stretch planetary orbits and weaken a star's grip on its outer worlds. Combined with internal gravitational chaos, the conditions for planetary ejection appeared not rare, but inevitable. By the mid-1990s, the question facing astronomers was no longer theoretical. If planetary systems naturally eject planets, then the galaxy should already be filled with them. But proving that prediction required a method capable of detecting objects that produce almost no light at all. And that challenge would lead astronomers to one of the most unusual observational techniques in modern astronomy, one that relies not on light emitted by a planet, but on the subtle way gravity can bend the light of distant stars. The key to finding these invisible worlds was hidden inside Einstein's theory of relativity, and it would soon transform the search for the loneliest planets in the universe. In 1915, Albert Einstein published a theory that quietly rewrote our understanding of gravity. According to general relativity, mass does not simply pull on objects, it bends the fabric of space-time itself. Light travelling through that curved space follows the bend. Under the right conditions, gravity can act like a lens. For decades, this prediction remained a mathematical curiosity. Then, in the 1990s, astronomers realized it could become a powerful tool. If an unseen object drifted in front of a distant star, its gravity would briefly focus the star's light toward Earth. The star would brighten smoothly, then fade back to normal. The object causing the effect might remain invisible, but its mass would reveal itself through the shape and duration of that brightening. This phenomenon is called gravitational microlensing. In 1992 and 1993, large monitoring programs began turning this idea into an observing strategy. Projects such as the Optical Gravitational Lensing Experiment, OGLE, operated by astronomers at the University of Warsaw, started watching millions of stars toward the dense center of the Milky Way. Every night, automated telescopes scan the same crowded star fields, searching for tiny changes in brightness. The method required patience. Most stars remained steady for years, but occasionally a star would brighten for several weeks. These were micro-lensing events caused by ordinary stars passing in front of background stars. Then something unexpected began appearing in the data. Some brightening events were far shorter than expected. Instead of lasting weeks, they lasted only a few hours. In rare cases, the signal lasted less than a day. When astronomers modelled these brief flashes, the results pointed to masses far smaller than stars. Planetary masses. Even more surprising, careful follow-up observations revealed no host star nearby. If a star had been present, its gravity would have distorted the microlensing signal. But the curves were clean, simple, and isolated. The simplest explanation was also the most unsettling. The objects causing these signals were planets travelling through space alone. By the early 2000s, several research teams analysing OGLE and MOA survey data began publishing evidence for what they cautiously called unbound planetary mass objects. Astronomers avoided the word planet at first, aware that the implications were enormous. If the interpretation was correct, the galaxy contained a hidden population of worlds that did not orbit any star. Invisible planets were passing silently between the stars, revealing themselves only through brief distortions in starlight that lasted hours before disappearing forever. In 2012, astronomers encountered an object that refused to fit neatly into any known category. It appeared during the Canada-France Brown Dwarf Survey, a project designed to search for faint substellar objects using powerful infrared telescopes. Researchers expected to find brown dwarfs, objects heavier than planets but too small to ignite sustained nuclear fusion like stars. But one discovery stood out immediately. Catalogued as CFB-DSIR2 149-0403, the object was located roughly 130 light-years from Earth. It moved through space alone, with no visible star nearby. At first glance, its faint infrared glow suggested a cold brown dwarf. Yet the deeper astronomers looked, the stranger it became. Measurements of its brightness and temperature indicated a mass between 4 and 7 times that of Jupiter. That number mattered enormously. Astronomers often use the deuterium burning limit, about 13 times the mass of Jupiter, as the dividing line between planets and brown dwarfs. Objects above that mass can briefly fuse deuterium. Objects below it cannot. CFB-D SIR2 149-0403 fell far below that threshold. Its atmosphere revealed methane and water vapor, chemical fingerprints commonly found in gas giant planets. Its radius matched predictions for young giant planets rather than aging brown dwarfs. Everything about the object suggested a planetary nature, except for one problem. Planets, by traditional definition, orbit stars. CFB DSIR2 149-0403 did not. The discovery sparked immediate debate among astronomers. Some researchers argued that without a host star, the object should be classified as a low-mass brown dwarf. Others pointed out that formation history, whether an object forms inside a planetary disk or collapses directly from a gas cloud, may matter more than location. The International Astronomical Union, the authority responsible for astronomical classifications, faced a growing dilemma. If objects like CFB DSIR2 149-0403 were truly planets, then the long-standing definition of a planet would have to expand beyond stellar systems. Meanwhile, additional surveys were beginning to detect more isolated planetary mass objects across the galaxy. Each discovery made the debate harder to ignore. The evidence suggested that planets could exist entirely on their own, born within solar systems and later expelled into interstellar space. But even this discovery represented only part of the story. CFB DSIR2 149-0403 was a giant planet, massive, warm, and still glowing faintly from its formation. The real surprise would arrive when astronomers detected something far smaller, a world with a mass similar to Earth, revealed by a signal that lasted less than an hour. And that fleeting signal would change the scale of the rogue planet population forever. In 2016, astronomers saw something that lasted only 42 minutes. For most discoveries in astronomy, scientists have days, months, sometimes even years to analyze an event. But this signal appeared, brightened a distant star, and vanished in less than the time it takes to watch a single film. Yet that brief moment revealed one of the most astonishing discoveries in modern planetary science. The signal was detected by the optical gravitational lensing experiment, known as OGLE, one of the world's longest-running microlensing surveys operated by astronomers at the University of Warsaw. Night after night, OGLE's telescopes monitor millions of stars toward the crowded center of the Milky Way, searching for tiny changes in brightness caused by invisible objects drifting in front of them. Most microlensing events last weeks. A massive star bends the light of a background star slowly, producing a long, smooth rise and fall in brightness. Even Jupiter-mass planets typically create signals that last several hours. But this event was different. It lasted just 42 minutes. The object responsible was later catalogued as OGLE-2016-BLG-1928. When astronomers analysed the light curve, the precise shape of the star's temporary brightening, they found that only one kind of object could produce such a short event, an object with roughly the mass of Earth. That result carried enormous consequences. Until this point, most models suggested that if planets were ejected from their systems, they would usually be large gas giants. Smaller rocky planets were expected to collide with other worlds, or fall into their stars long before they could escape. OGLE-2016-BLG-1928 proved otherwise. Somehow, a planet roughly the size of Earth had been thrown out of its original planetary system and was now travelling alone through the galaxy. The discovery was announced in 2020 in research led by astronomers analysing OGLE survey data. The conclusion was cautious but unmistakable. The clean microlensing signal showed no trace of a host star. If one had been nearby, the light curve would have been distorted. Instead, the data revealed a solitary planetary mass drifting through interstellar space. The event could never be observed again. Microlensing alignments happen only once. The planet itself is now somewhere else in the Milky Way, invisible to every telescope on Earth. But the implications of that 42-minute signal were profound. If a survey observing only a tiny portion of the sky could detect one Earth-mass rogue planet, then the galaxy may contain vast numbers of them. The question facing astronomers was no longer whether rogue planets exist, it was how many of them are out there, and the answer would soon force scientists to reconsider what may be the most common type of planet in the entire Milky Way. By the end of the 2000s, astronomers began confronting a possibility that sounded almost unbelievable. The lonely planets discovered so far might represent only the smallest visible fraction of a much larger population. Microlensing surveys like OGLE and MOA observe millions of stars, but they still monitor only a tiny portion of the Milky Way at any moment. Each detection is a rare alignment between a distant star, an invisible planet, and Earth. The geometry must be perfect. If the timing is missed by even a few hours, the signal disappears forever. Yet despite these limitations, rogue planet signals kept appearing. Astronomers began to ask a statistical question. If a survey watching only a narrow patch of sky can detect several rogue planets, how many must exist across the entire galaxy? To answer that, researchers performed population analyses using years of microlensing data. One influential study published in 2011 by an international team working with the MOA collaboration analysed thousands of lensing events toward the galactic bulge. Their conclusion was striking. There could be at least as many rogue planets as there are stars in the Milky Way. Some models suggested even higher numbers, perhaps 2 or 3 rogue planets for every star. Considering that our galaxy contains roughly 100 to 400 billion stars, the implication was staggering. The Milky Way may contain hundreds of billions of planets drifting through interstellar space. Most of them are completely invisible. They emit almost no light and reflect none. They reveal themselves only briefly by bending the light of distant stars before vanishing again into darkness. This realization forced astronomers to rethink a basic assumption about the universe. For centuries, planets were believed to be rare companions of stars, small members of larger cosmic families. But the new data suggested something very different. Planet formation may produce more worlds than stars can keep. Gravity sorts the survivors from the exiles. Some planets remain bound in stable orbits, forming systems like our own solar system. Others are flung outward during the chaotic early stages of planetary formation, escaping forever. The galaxy we see at night, filled with shining stars, may hide an even larger population of unseen planets moving silently between them. But these wandering worlds are not necessarily frozen, lifeless objects. Deep inside some rogue planets, powerful processes may still be generating heat. And under the right conditions, even a planet without a star might sustain environments far more complex than scientists once imagined. To understand that possibility, astronomers had to look beyond how rogue planets are detected and begin asking a new question. What are these isolated worlds actually like? Imagine a planet drifting alone between the stars, cut off from sunlight forever. At first glance, such a world seems destined for permanent darkness and frozen silence. Without a star to warm it, logic suggests its surface would quickly drop toward the coldest temperatures possible in space. For many years, scientists believed exactly that. But in the early 2000s, planetary physicists began reconsidering this assumption. Studies of planetary interiors, supported by work from NASA and several international research groups, revealed that planets do not depend entirely on stars for heat. Deep inside many worlds, powerful energy sources continue to operate long after their formation. The most important of these is radioactive decay. Inside rocky planets lie unstable elements such as uranium-238, thorium-232, and potassium-40. These atoms slowly break apart over billions of years, releasing energy as heat. On Earth, this process contributes a large portion of the heat, driving volcanic activity and plate tectonics. On a rogue planet with no sunlight at all, radioactive decay could become the dominant energy source. The numbers are surprisingly large. Uranium-238 alone has a half-life of more than 4 billion years. That means a planet formed early in the history of the galaxy could still be generating internal heat today. In 1999, planetary scientist David J. Stevenson of the California Institute of Technology proposed a remarkable idea. If a rogue planet retained a thick hydrogen atmosphere, that atmosphere could trap heat rising from the interior, acting like a powerful insulating blanket. Under the right conditions, the surface temperature of such a world might remain far warmer than expected. Hydrogen behaves differently from gases like carbon dioxide. When hydrogen molecules collide under pressure, they can absorb infrared radiation and prevent heat from escaping easily into space. This process, known as collision-induced absorption, allows hydrogen atmospheres to trap heat extremely efficiently. In simple terms, a rogue planet might wrap itself in its own thermal blanket. Instead of cooling rapidly, the planet would lose heat slowly, over billions of years. That possibility changed how astronomers began thinking about isolated planets. These worlds might not be completely frozen after all. Beneath thick layers of atmosphere or ice, internal heat could sustain geological activity and complex chemistry. But the most intriguing implication lies even deeper. If heat remains trapped beneath an insulating surface, something extraordinary may form below the frozen crust. Hidden oceans. And in the darkness beneath kilometers of ice, these subsurface seas may represent some of the most isolated environments in the universe. To understand how such oceans could exist, scientists began comparing rogue planets with a surprising set of worlds much closer to home. In 1995, NASA's Galileo spacecraft sent back data that would change how scientists think about life in the universe. The spacecraft was studying Jupiter's icy moon Europa when it detected something unexpected. Beneath Europa's frozen crust, hidden under kilometers of ice, scientists found strong evidence of a vast liquid ocean. It was a startling realization. Europa receives very little sunlight. Its surface temperature averages around -160 degrees Celsius. Yet deep below its icy shell, liquid water appears to exist. The reason is simple. Heat from inside the moon prevents the ocean from freezing solid. Over the following decades, similar discoveries followed. Saturn's moon Enceladus revealed geysers of water vapor erupting through cracks in its icy crust. Observations from the Cassini spacecraft confirm that a global subsurface ocean exists beneath its surface. These worlds demonstrated something profound. Liquid water does not always require a nearby star. By the early 2000s, planetary scientists began applying the same physics to rogue planets. If small icy moons could maintain hidden oceans using internal heat, then larger rogue planets drifting through interstellar space might be capable of the same thing. In fact, the conditions could be even more favorable. A rogue planet the size of Earth would contain far more radioactive material than Europa or Enceladus. That means greater internal heat production over billions of years. If the planet also possessed a thick ice layer or a hydrogen-rich atmosphere, that outer shell would act as insulation, slowing the escape of heat into space. In simple terms, the planet would freeze from the outside in. The surface would become a hard, frozen crust exposed to the darkness of interstellar space. But deep below that crust, pressure and internal heat could maintain a layer of liquid water for enormous stretches of time. Computer models developed in the early 21st century suggested that these oceans might survive for billions of years beneath the frozen surfaces of rogue planets. These environments would be completely isolated from sunlight, yet they would still contain water, heat, and potentially the chemical ingredients necessary for complex reactions. On Earth, similar environments already exist. Deep beneath the ocean floor, hydrothermal vents support ecosystems that thrive without sunlight. Microorganisms there rely on chemical energy released from the planet's interior rather than photosynthesis. If such chemistry can support life in Earth's deep oceans, scientists began asking an unsettling question. Could similar processes occur inside rogue planets drifting through the galaxy? The possibility does not prove that life exists in these environments, but it expands the places where life might be able to survive. And if rogue planets are as common as current observations suggest, then these hidden oceans may not be rare at all. They may represent one of the most widespread habitats in the Milky Way. But rogue planets are not the only worlds that live in near-total isolation. Some planets still orbit stars, yet exist so far away from them that they experience conditions strikingly similar to rogue planets, and these distant worlds reveal another path toward planetary isolation. Not every isolated planet is completely alone. Some worlds still orbit stars, but at distances so vast that their suns barely matter. In 2008, astronomers studying young star systems made a puzzling discovery. Using powerful infrared telescopes in Chile and Hawaii, researchers began identifying giant planets located thousands of astronomical units from their parent stars. 1 astronomical unit is the distance between Earth and the Sun. Neptune, the outermost major planet in our solar system, orbits at just 30 astronomical units. These newly discovered planets were found at distances of 1,000 astronomical units, 2,000 astronomical units, sometimes even farther. At such distances, the parent star becomes little more than a bright point in the sky. The light reaching the planet is incredibly weak, often weaker than the faint background glow of the galaxy itself. Astronomers began referring to these worlds as ultra-wide orbit planets. One striking example is Gu Piscium b, discovered in 2014 by an international team of astronomers using data from the Gemini Observatory. This massive planet orbits its host star roughly 2,000 astronomical units away, about 60 times farther than Neptune is from our Sun. At that distance, the planet takes tens of thousands of years to complete a single orbit. From the planet's perspective, its star would barely warm the surface. Day and night would have almost no meaning. The environment would resemble interstellar space more than a typical planetary system. These discoveries raised an important question for planetary scientists. How could planets end up so far from their stars? Traditional models of planet formation suggest that planets form inside dense disks of gas and dust surrounding young stars. But those disks rarely extend beyond a few hundred astronomical units. Planets forming thousands of astronomical units away should be nearly impossible. The most likely explanation is gravitational scattering. During the chaotic early stages of planetary formation, interactions between massive planets can fling one of them outward. If the ejection velocity is just slightly below escape speed, the planet remains loosely bound to the star. Instead of becoming a rogue planet, it ends up trapped in an enormous orbit at the very edge of the system. These ultra-wide orbit planets exist in a fragile balance. Their connection to their stars is extremely weak. A passing star, a nearby molecular cloud, or even slow gravitational tides from the Milky Way can eventually disrupt their orbits. Given enough time, many of them may be pushed beyond the limit where their star's gravity can hold them. At that moment, they become something else entirely, a rogue planet. These distant worlds represent the final boundary between planetary systems and interstellar space, and understanding them leads to a deeper realization about the structure of our galaxy. Because when astronomers step back and examine the full population of rogue planets, ultra-wide orbit worlds, and star-bound systems together, a startling picture begins to emerge. In the early 21st century, astronomers began to realize that the night sky might be hiding far more planets than anyone had imagined. For thousands of years, humanity looked up and saw stars as the dominant structures of the universe. Planets were considered rare companions, small bodies bound tightly to the gravitational pull of their suns. But discoveries over the past 3 decades have revealed a different picture. The Milky Way may contain not just billions of planets orbiting stars, but hundreds of billions that wander freely between them. This conclusion did not emerge from a single discovery. It came from years of data collected by international surveys, such as the Optical Gravitational Lensing Experiment and the MOA collaboration, combined with theoretical models of planetary system formation developed by research institutions around the world. Together, the evidence points toward a remarkable possibility. Planetary systems may create more planets than they keep. During the chaotic early stages of formation, giant planets tug on each other through gravity, scattering smaller worlds outward. Some remain trapped in distant orbits, barely connected to their stars. Others gain enough speed to escape completely, becoming rogue planets drifting through interstellar space. Over billions of years, this process repeats again and again across the galaxy. every unstable system adds new wanderers to the darkness between stars. The result is a hidden population of worlds moving silently through the Milky Way, planets that receive no sunlight, that orbit nothing, and that may travel for billions of years without ever encountering another star. And yet, as scientists have begun to understand, these planets are not necessarily lifeless frozen rocks. Some may retain thick atmospheres that trap heat from their interiors. Others may hide vast oceans beneath frozen shells of ice, warmed slowly by radioactive decay deep within their cores. If such environments exist, they expand the range of places where complex chemistry, and perhaps even life, might persist. The implications are profound. Habitability may not be limited to the narrow zones around stars that astronomers once considered essential. Instead, the galaxy may contain countless isolated environments where warmth, water, and chemistry continue far from any sunlight. In that sense, rogue planets represent more than just the loneliest worlds in the universe. They reveal something deeper about how planetary systems evolve. Stars create planets. Gravity decides which ones remain. The rest become travelers. And somewhere in the vast darkness between the stars, untold numbers of these silent worlds continue their journeys, unseen, unlit, and almost unimaginably alone.